Alright, today's problem is bitwise AND of a numbers range. So they give us a range from m to n, and we want to bitwise each number within this range that's inclusive, and then output the result. So for example, with 5, 6, 7, what we have is, here is our 5, 6, 7, and here's the binary representation of 5, 6, and 7. And then what we want to do is we just want to AND every number together. So we first AND 5 and 6. So here we have an and using this chart, we can see 1, 0 produces a 0, so 1, 0. 0, 1 also gives us a 0, and then 1, 1, we have 1. So that's 5 and 6, and now we want to AND it with 7, so 7 is 1, 1, 1, and this gives us 0, 0, 1, and this is binary for 4. So our output is 4. But if we do it this way of just ANDing each number, when we have a range, for example, from 1 to 2 billion, we will have to AND through 2 billion numbers, which will take a very long time. So this is not the most optimal way of solving this problem. Instead, if we realize two main observations, we can solve this in a lot faster. So let's look at a more complicated example. Let's say we have a number like 1, 1, 0, 0, 1, 0, and then we have another number that's 1, 1, 1, 0, 0, 0. So I don't really know what these numbers are. Maybe we'll do it something like this. And it doesn't matter because we need to just work in bits now. So we want to figure out the range from here all the way to here. So we want to AND each number in between here. And this gives us some result. So the first observation is that the common prefix for both of the numbers, so here is a common prefix, they both have 1, 1 to start off. This will never change, So if we get a 0 in any of here, that means that this is a smaller number, so it should have been up here, right? Because we see zeros before we see ones. If we build up our binary numbers, 0, 0, 0, and then we see 0, 0, 1, and then we see 2, and you see we always see zeros first, and then we see a 1. So if we were to see a 0 here, that means this must have been a smaller number, so it can't exist in here. Okay, so this tells us that in our solution, these two bits have to be 1. Now what about the rest? So for the rest, what we'll do is we'll see when this switch happens from a bit of 0 to bit 1, and what we claim is that we must have seen this number somewhere in between. Because in order to flip the bit, we must see that. So let's go back to our example. 0, 1, 2, 3 will have this, 4 will have this. So you can see here we flip the bit from 0 to 1, and when we flip this bit, we have this, all zeros here. So that means when this happens, looking at our list of bitwise AND, whenever we see a 0, so whenever we see a 0, the output is always 0 no matter what. So the moment we see a 0 here, we know that these numbers will forever be zeros no matter what. And then this number itself, because we're going from 0 to 1, we know that this also has a 0. So now our question turns from bitwise AND each number of the range into find the common prefix of m and n. So let's continue with the example that we had. We had 1, 1, 0, 0, 1, 0, and we had 1, 1, 1, 0, 0, 1. Okay, so what other bit manipulation tricks do we have to find the common prefix? Well, we're going to use something called a right shift. So this is a right shift. And how you can imagine a right shift is, let's imagine you have some sort of a boundary here. And then when you right shift it by 1, what you do is you have your numbers. And then when you right shift it by 1, you make it cross the boundary. And everything that's after the boundary gets eaten up. So everything here after the boundary gets eaten up. So we create two new numbers that's this one and this one. So we're going to continue doing this right shifting. And what we're aiming for and when we'd like to stop is when they have the same value. So here, the value here are equal. They're both, the decimals 3. And that's the point that we're aiming for. So when this happens, we know that only we have the common prefix, because the common prefix will have the same value once we shift everything away. So all of these is x now. Okay, so now we have this common prefix, but this, in terms of place, is not in the right place, because now we have our common prefix all the way here, but really we want to shift it all the way back to 1, 1, where it belongs. So how do we do that? Well, now we'll do something called left shift. So it'll look like this. And then we'll left shift it by exactly the amount that we right shifted by. So here we right shifted 4 times. So what we'll do here is we'll left shift it 4 times. So here's what we have currently, and then we'll left 1, 2, 3, 4. This puts us back to where we belong. And each time as we left shift, because it's coming from the end, what happens is that they just get filled with zeros. So this gives us our solution. So all we have to do is, so basically our main algorithm will become 1, shift right until they're equal, and then 2, shift left back to where they belong. Okay, well, let's just code it out. It's going to be very short. So we'll start with some sort of a way to keep track of how many times we've shifted. And while m does not equal n, so while their prefix is not equal yet, so we haven't found the common prefix, we will shift it to the right by 1, and we'll shift n by the right by 1. Okay, and then we'll increment our count, meaning that we've shifted it. Now at this point, we found the common prefix, and now we want to shift it back. So return m, and we'll shift it back by the amount that we shifted it to the right by. We'll shift it to the left. Okay, so that should be all there is to it, and it'll be accepted. Okay, so a brief runtime of this. An integer has 32 bits. So that means at most, if we shift right by more than 32 bits, then we've essentially zeroed out both integers. So that means at most, we'll only have to shift right 32 times, probably even less. And then this is constant. So this 32 is a constant. It's not related to our input m or n. And these are all constant operations. So in total, this function is actually just has a runtime of constant. Okay, that's it for today, and I'll see you on the next one.